In this class we are going to discuss about the next concept, that is state reduction and state assignment. So in that, first we will go with the state reduction method, and after that we will go with state assignment method. Okay, so here this state reduction and state assignment method, which is a part of design of the sequential circuit. Okay, so basically state reduction can helps in reducing the number of flip-flops. Okay, so the number of flip-flops required will be depending upon the number of bits in each state. Okay, so when the number of states are reduced, there is a chance of reducing the number of bits that can be used to represent each state. Okay, so hence the number of flip-flop will be reduced. So here we are going to consider that like two states, when we say they are similar, then we can reduce one state. So here clearly I mentioned, that is, if two states are said to be similar or equivalent, so that means every possible set of inputs generate exactly same outputs and same next state also. Like this, if you are having state diagram, no, so for example, whatever the state diagram you are having, okay, see here, this is the one state diagram, sorry, state table. So in that state table, how many states we are having here? Present state, next state and input output, right? So that means here, if the present state having the inputs, so that will be having the similar possibilities or having, so that similar possibilities will be equal to the next state also. So then we can eliminate any one state in that. So that is the meaning of state reduction here. So if two states are said to be similar or equivalent, we can reduce any one in that. Okay, so we can reduce any one state in that. But before going to reduced, compulsory we have to check it whether the next state and also output state will be equal or not. We have to check it, that one. Okay, so that is the method we have, the state reduction. Okay, so that means one state will be eliminated and one state will be retained here. So how can we say that the two states are equivalent? Means that is nothing but for each member of the set of inputs, they give exactly the same output and send the circuit either to the same state or to an equivalent state. Okay, so how can we say that the two states will be equal? Means, so clearly mentioned, so that is nothing but for each member of the set of inputs, that gives the exactly the same output as well as same next state also. Okay, so that is called as the state reduction method. So now we'll see here, we'll have one example. With the help of that example, we have to explain the state reduction method. Okay, so state assignment we'll discuss later after completing the state reduction, then we'll go with the state assignment. Okay, so see here we'll have an example. So for this example, it will be clearly mentioned, that is one we have one state diagram. Okay, so in state reduction method, directly they given one state diagram or maybe state table they given. Okay, there is no logic diagram here in this procedure. We have directly the problem is given like a state diagram or the problem is given like a state table. Okay, so if you are having state diagram, no, that you can convert it into the state table, or they given directly state table, no need to consider the state diagram. Okay, clearly I mentioned ma, so that is nothing but if the problem is like having state diagram, first you should convert it into the state table, then only you can reduce the state. Okay, so after converting the state table, then the procedure you will start, whatever the state reduction procedure you have, that will be start. Okay, so after converting the state table, then only the state reduction is possible. So if in case there is no state diagram, directly the problem is given like a state table, so you can directly start with state table only, no need to consider again state diagram. Okay, so here we have the state diagram actually. So you know, this state diagram consists of the how many states actually? 1, 2, 3, 4, 5, 6, 7. So state diagram, this state diagram consists of totally 7 states. You know, right? Each state can be represented in a circle notation. So in the circle, whatever the state you are having, that is our present states. Okay, so now I can draw the state diagram, state table here with the help of that state diagram. Okay, so first I will convert this state diagram into state table. First clearly I will mention here one thing, that is nothing but in the circle how many states, that means how many alphabet letters you are having that in the circle, so that you can consider as the present states. Okay, so clearly mention the present state values will be always mentioned in the circle notation, that we can call it as the state. Okay, so here I can mention present states. So you know already state table describes the present state, input, next state and output also. If the output will be there, then you can mention. So if output is not there, you can skip this part. So compulsory the state table will be describes the 4 states. So first will be present state completed. So now coming to the input part. Okay, so input is having single variable, no, then it will be exist as 2 combinations, either 0 or 1. So directly I can say that here the input value will be represented as here, and the next state I clearly mentioned. Okay, so now will be mentioned as variables here, what is the present state variable and what is the input variable, what is the next state variable. That means we can represent it in a letters, alphabet letters we can represent here. Okay, so here I can mention present state already they given, the in each circle we have the small alphabet letters that you can place it as it is. Okay, so the present state values will be A, B, C, D, E, F, G. Okay, so these are the present state values we are having, already they mentioned in the circle. So this is the each and every state of present state. Now we'll mention as input here. So you know, right, for each directed line having the above the directed line we are having the transitions from one state to another state, right? So this transition, whatever the line we are having, so each and every line will describes as the transition between each and every state. Okay, so that means here whatever the slash before line and after line, before the slash value whatever we are having, that will be considered as input, and after the slash whatever the value we are having, that will be considered as output, right? So that means all transition will be having the inputs and output values, right? So first you should mention the input values here. So input for the, if you are taking one state, so it consists of 2 transitions. So like for example I am taking the state as A, it will be consisting the 2 transitions here, A itself having and also A to B transition we are having. So that means the input 0 will be there and the input 1 will be there. So 2 transitions will be there for input. So one is x is equal to 0 and x is equals to 1. So input x is equal to 0 and input x is equal to 1. Okay, you can imagine x, that input as x. Okay, so one value is 0 and another value is 1. So now coming to the next state. So next state is nothing but here again we have to clearly say that the next state value we can say that here output value. Okay, it's approximately equal to the output value I clearly mentioned. So that output is nothing but here again we have to 2 transitions from output. So that is nothing but sometimes we are having the output value is 0 and sometimes we have the output value is 1 also, right? So it may be consist of x is equal to 0 and x is equal to 1. Okay, input as will be considered as x only and output will be considered as x only, but the transition will be takes from 0 to 1 and 0 to 1. So now we'll be write it as input values here. First the transition will be A. So A will be having itself only the first transition, that is input value will be 0 and the output value will be 0. So that means whenever the x value will be 0, the transition will be itself only. So that means the A transition, if the input is 0, then only we are getting the state as again A only. So in that case, okay, A, whenever the input value is A only, but the output what is that? 0. So output here you mention like that for x is equal to 1. So x is equal to 1 means input value no here. So A will be transition from A to B. So that is nothing but whenever the x is equal to 1, the A transition will be takes as B. But what about the output value? This output value is 0. Like this, coming to B. So B transition will take it as whenever the input is 0, this transition will comes to the C. So that means B value whenever the x input is 0, so it will goes to the C value. In that case, whenever it reaches the C value, what is the output value? 0. And coming to next B value. So whenever the B value takes as input 1, so what is the transition? So B value takes the 1 input. So that means before the slash you have to observe input value always. So 1 means it reaches the transition is D. So then output value is what? Again 0. Like that, coming to C. So C will be takes as input 0. So but the transition will reach us to the A. So C to A when the input is 0. In that case output is what? 0 only. So coming to C, the next transition 1. So C to D will get the 1. Input as 1 and the output is what? 0. Like that. D to E is the input 0 and output is 0. D to E, the input is 0. Okay, so input is 0, the transition will be D to E. And what is the output? 0 only. Next, D to 1 transition is nothing but F. The output is also F. Sorry, 1. Okay, now coming to E value. So E will be 0, that transition will reach us as A. So whenever x is equal to 0, it reaches transition A and the output is 0. And E to F, the transition will be, output will be 1. Okay, so now coming to F. So F reaches the input 0, the transition will reach us to Z. Input is 0. Next, F itself 1 only, the output will be 1. So F itself 1 when the input is 1, so output is also 1. So coming to last one, Z transition. So Z transition for 0 input, it reaches the A transition. The output is what? 0 only. And next, okay, so G to 1 transition we have to observe. When the input is 1, it reaches the F and the output is also 1. So this is the state table we are getting. So like this you have to find out whenever the state diagram you are having in state reduction method, that will be converted into the state table into like this. Okay. So you have to verify input values and output values, and also for input that means what is the transition. Okay, you have to mention in that part. So after getting the state table from the state diagram, so then we'll go with the next step, that is nothing but state reduction method. So we have to reduce the number of states in state table. So how many states are similar in this state table, we have to identify that states. Okay, so now let us start the state reduction procedure. Okay, so in this state table we can observe that E and G states are similar. Okay, see here, E and G states are similar. You can observe that it is having the same next state and same output also. So see here, E value having the input is AF and the output is 0, 1. Like that, G value also, input is AF and the output is 0, 1. So that means here it is having the same next state and the same output for all combinations of the inputs, that is x is equals to 0 and x is equals to 1. So in this case we are eliminating G. Okay, so in this case we are eliminating the G, and wherever we are having the next state G in this case, okay, wherever we are having the next states G, will replace with as E only, because here G is eliminated because E and G will be same. So that's why we can eliminate the G path, and remaining states wherever we are having the G path, okay, so wherever we are having the G path here, that will be eliminated as E. Okay, so that will be replaced with E. Now again we'll observe this, if there are any other states will be similar. Okay, so now again we will observe after eliminating this G value. So again we will observe here. Now if any states will be similar or not. So now you can observe here that D and F are similar. D and F are similar. So F is eliminated and F is replaced with D, because here D is having EF and F is also having EF after eliminating G, right? So and in output values 0 1 0 1. So that's why D and F will be similar after eliminating the G. So then we can eliminate the F state. Okay, so then we can eliminate this F state. So then wherever we are having the F value, that will be eliminated with, or that will be replaced with D state. Okay, so now we have to observe again if there are any similar states. It can be observed that there are no similar states here. Okay, so after eliminating F and G, again you have to observe whether the similar states will be there or not. Okay, so one thing you have to observe here, we are having same next state for the C and E. See here, C and E is having AD and 0 0 and 0 1. So but coming to here, C of the outputs are 0 0 and but in the case of E of the outputs are 0 1. Right? So we can't consider that as similar case. So further it cannot be reduced. So compulsory, if you want to reduce the state, means next state input case, that means next state and output case both will be equal. Okay, so then only we can reduce the states. In both the cases, that means in both the states anyone state cannot be having similar. So compulsory we cannot eliminate it. Okay, so remember that one. So further we can't be reduced this state diagram. So finally we are getting the state table is like this. So after eliminating F and G, we can reduce the state table is, that means here two states are reduced, present state, and the input will be x is equal to 0, x is equal to 1, and the output x is equal to 0, x is equal to 1. So now write the as it states A, B, C, D, E. So F and G already eliminated now. So for AB 0 0 and CD 0 0, AD 0 0 and E, here F is eliminated now. So in the place of F we have to write it D. So ED 0 1 and here also F reduced. So AD 0 1. So finally we are getting the state table is like this. After reducing the two states, then we are getting the output is like this. So what is meant by state reduction here? If any two states are having these similar possibilities, so then you can eliminate that state, and whatever the state is eliminated, wherever we are having that possibility in the state table, that will be replaced with another variable. Okay, so you can place it like this. Here first thing is E and G's possibility will be having same AF and 0 1 0 1. So directly we can eliminate G. So in the state table wherever G is there, so that G is eliminated with, that G is replaced with E, like that. In the second possibility D and F will be same, that's why we can eliminate F with D. Okay, so wherever we are having the F, that will be replaced with D. So after that, here the E possibility and C possibility will be same, but in the output path both will be different. Input is same AD, but the output is not matched. So that's why we cannot reduce the two states. Okay, so this is the state reduction method. So totally the 7 states can be reduced into the 5 states. If it is possible, if any possibilities will be there, like similar possibilities will be there, so again you have to reduce that states. Okay, so if there is no chance, you can leave it up to that. Okay, so totally here we can observe 7 states can be reduced into 5 states. So the reduced state table is like this. Okay, so this is the procedure of the state reduction method. Okay, so now we have to move on the state assignment method. So after finding the state reduction, then we'll go with the state assignment. So what is meant by state assignment means to represent states in the state diagram using binary values instead of alphabets. Here already we have state diagram. So this state diagram can be represented each and every state as alphabets, right? So A, B, C, D, E, F, G, like that. So that means here each state in the circle whatever we are having, that each state can be represented in alphabets actually in state diagram. But while coming to state assignment, if you want to implement that state assignment, so compulsory whatever the alphabets you are having, that will be replaced with binary values. Okay, so that is called as the state assignment. So now we'll find its state assignment for the state table. So instead of alphabets, we'll write it binary values or binary numbers. Okay, so remember this point. So here if you observe the state table, here the states are represented using alphabets such as A, B, C, D, E, right? So we can't produce further when the states are represented as alphabets. So we are supposed to assign some binary representation to it. Okay, so as such that there are no conditions that what values we are supposed to assign each and every state. Okay, so that is like binary values we have to assign the each and every state. So but it is always better to go for minimum number of bits that can be used actually. Okay, so how to take that binary values means here. So first of all find count it how many states we are having. So 1, 2, 3, 4, 5. Okay, so here we have one formula for state assignment. How to assign the binary values means here how to take the binary values means for that we have one formula. So that is nothing but for a circuit if having m states, m number of states, so then the codes must contain n bits. Okay, so the codes must contain n bits. So where 2 power n is greater than or equal to m, this condition is satisfied. How to take the binary values, whether 2 number of possibilities we have to take or 3 number of possibilities we have to take, or whether the 4 number of possibilities are take means we don't know exactly, right, how to take that values binary numbers. So for that we have to take one condition, that is 2 power n is greater than or equal to m here. Okay, so where in this case small m is nothing but m states. M states means how many states you are having? 5 states, right? So where m is equals to 5. Okay, so that means here we have to this m value we have to place it on this formula. So then we may get it as 2 power n is greater than or equal to 5. So that means if you are substituting n is equals to 1, 2, 3, that means natural numbers if you are substituting in the place of small n, so compulsory the condition is satisfied like this. So for example if you are taking n is equals to 1, so 2 greater than or equal to 5, that condition is not satisfied. If you are taking n is equals to 2, so then 2 square, so that means we are getting 4. 4 greater than or equal to 5 is also not satisfied, that is also not correct. And coming to if you are substituting n is equals to 3, so 2 cube means 8, 8 is greater than or equal to 5. So that means this condition is satisfied, right? So for that case we have to take it small n value will be as 3. So then we may get it as 2 cube. So then 8 is greater than or equal to 5. So then only the condition is satisfied. So here what is meant by small n means that will be represented as binary codes. Okay. So that means here we have to take it as 3-bit code. 3-bit binary codes we have to take it. So using 3 bits, 8 combinations are possible. So out of which any 5 you can be used. Okay, here 8 possibilities we are getting now. So that 8 possibilities you should consider as 3-bit code: 000, 001, 010, 011. Up to how many possibilities we have to take it? 8 possibilities. 100, 101, 110, 111. So 3, 6, 8. Right? So in that 8 possibilities, out of 8, how many possibilities we have to choose? Any 5. Okay, so using 3 bits, 8 combinations are possible, out of which any 5 can be used to represent the 5 states. Okay, so here I am assigning for state A, first state. Okay, for small a of state, I can assigning the number as 000, and for B I am assigning the binary state as 001. Like that for C, 010. Like that D, 011. For E, 100. For F, 101. Okay, 010, 011, 100, 101. Totally we are having up to E states only. No need to consider the F value. We have only 5 only. 1, 2, 3, 4, 5. So totally 5 states are completed. So when we assign this particular binary values to the particular states, okay, and the previous state diagram we are replacing with alphabets to the given binary values, then we will get the state table. Okay, so now again we have to draw the state table. That means the replacing the state values. So present state, input and output. So input x is equal to 0, x is equal to 1, and output x is equal to 0, x is equal to 1. So first write it present state values a, b, c, d, e. So a, b, c, d, e we have already considered, that is binary words, that is a as 000 and b as 001 and c as 010 and d as 011 and e as 100. Like that, whenever the input is x is equal to 0, what are the values we are having? A, and the next one is for 1, b. So for a is nothing but what is the a we are having? 000. Here also we have to change that values. That means wherever you are having the alphabet letters, that will be replaced with binary codes. That is the state assignment. Okay, now that second one is CD. CD is nothing but C is 010 and D is nothing but 011. For this, as it is, you can place it as outputs also, that already in binary numbers 0000. So as it is you can mention, no need to change these values because already in binary case. Okay, now coming to the third state, C, that having AD and 00. AD, A is nothing but 000 and D is nothing but 011. So here again 00 we are having. Okay, so now coming to the D value, that is ED 01. ED, E is nothing but 100 and D is nothing but 011 and this will be 01. Okay, so last one is AD and 01. A is nothing but 000 and D is nothing but 011. So this is also 01. Okay, so this is the final state table we are collecting from the state assignment method. Okay, so whatever the binary states are represented in alphabets, that will be represented in binary codes, that is called as the state assignment method. So after reducing the states, so we'll go with the state assignment method. So that state assignment method will consist of the only binary codes. Okay, so this is the state reduction and state assignment method. So this is very important for next concept, that is we have a design of clock or sequential circuit. In that we should mention as the state reduction method. Okay, so this is the complete concept of the state reduction method. So we have to reduce the states. So whatever the states you are having, that will be converted into the binary form. Okay. So based on this formula, you have to taking the binary codes.